Okay, all good? Okay, let's look at the questions together. And thank you all for making it here despite the terrible weather. I feel like over the last couple of weeks, every Friday morning, exactly around 8:40, it just started to pour. And yeah, that's really bad, but thank you and for making it here. So the first question, the child test compares the fit of a single regression model across the entire data set to the fit of two separate regression models divided at a known breakpoint. So this is related to what we discussed on Monday. And do you think that this is true or false? Now think about what was the child test. Okay, the child test is essentially an F-test where we have incorporated breakpoint dummies into the model and its interaction terms. And the idea of the child test is to test whether the parameters associated with the breakpoint dummy, the one on the dummy alone and the ones on the interaction terms, whether they are jointly significant. And what actually is the intuition behind this test? Okay. I give you 5 seconds for a second thought, okay? When are you going to change your vote? 5, 4, 3, 2, 1. Okay. It seems like maybe some people has changed their idea, and now it's the majority that wins, okay? This is indeed a correct statement. What was the idea of the F-test? Okay, the child test is essentially the F-test. The construction of the F-test involves comparing the residual sum of square of the restricted and unrestricted model. Remember in the test here, okay, what we discussed on Monday, essentially under the restriction, okay, under the null hypothesis, the model will not involve these terms. Essentially, that means we'll have the same parameter for the entire data set, okay? Whereas the unrestricted model, it allows us to have different parameters, okay? Different intercept and different slope corresponds to different subsamples before and after the break, okay? Remember, F-test is about comparing the model fit, okay? Whether the model under the null hypothesis or whether the model under the restricted hypothesis, under the restricted model or the alternative hypothesis that actually fits the underlying full sample data well, okay? So therefore, this is a correct statement, okay? We compare the fit of a single regression model, the one under the null hypothesis, our restricted model, to the fit of two separate regression models, essentially the model under the alternative, okay? The unrestricted model, the one incorporates the dummy variable and its interaction term. We compare the fit of these two and to decide whether the model fit is so different enough to reject the null hypothesis of no structural break, okay? Remember, in the F statistic, okay, that involves comparing the RSS under the restricted model with the RSS under the unrestricted. That's the numerator divided by the number of restrictions, okay? And in the denominator, we have the RSS associated with the unrestricted model divided by the total degree of freedom in the model, okay? So it's really about comparing the model fit. This is a correct statement, okay? If you're unfamiliar with the F statistic formula, it's time to check the notes on topic 2. So for those who just came in, I give you 7 seconds to scan the QR code, okay? 7, 6, 5, 3, time's up. Now, the next one, which is related to what we've been talking again and again so far. So it says that persistence is irrelevant to the concept of stationarity in time series analysis. Can this be a correct statement? Okay. Now, on Monday, we sort of established that persistence and stationarity do not directly imply each other. But would that imply they are irrelevant? Okay, so here this is a false statement. Okay, persistence, of course, is relevant for the concept of stationarity. Remember, persistence is related to the ACF, the rate at which the ACF decays as the lag age increases. Okay, and stationarity, one of the conditions requires that we have a constant autocorrelation structure. The constant autocorrelation structure is inherently related to the ACF, okay? So in a sense, the constant autocorrelation structure basically requires the degree of persistence to be stable over time, okay? If it were weakly persistence, let's say in 2000, it has to be continually weakly persistent to the same degree in 2015, okay? So persistence is relevant to the concept of stationarity. It's just that they do not directly imply each other, okay? So this is false. Now, the next one. A time series with trends can be considered weakly stationary if the trends are predictable. So this is kind of related to what we will discuss later today. But based on what we've seen so far, do you think this is correct or that's false? Okay, this is again a false statement. Think carefully what are the requirements of weak stationarity: constant mean, constant variance, constant autocorrelation structure. Remember, we've seen the time plots for series that has a trend. Okay? The trend is either going upward, going downward, which inherently means that the mean is changing over time. Okay? Therefore, the trends, even if it's predictable, it's only telling us that we can predict it to be going upward or going downward, in a sense that it's deterministic. But that definitely violates the constant mean requirement of weak stationarity, okay? And more importantly, regardless of the trends being predictable or not, as long as the underlying time series has a trend, the series is not stationary. We'll see in a bit, deterministic trend will imply a changing mean over time, whereas a trend that is stochastic, okay, that is random, will induces the variance and the covariances to change over time. Okay, so this is a false statement. Now, coming back to what we were discussing on Monday, structural breaks. So we've looked at the child test, which is the test for a known break date. And I'll spend maybe the next 10 minutes to quickly wrap up on detecting unknown break dates. So the focus of the lecture today is on trends, okay? So when the exact timing of the potential structural change, the tau, the value of the tau is unknown, we can no longer use the child test, okay? Because the child test requires a predefined value for tau. Then in this case, we would need to use a different approach to test for the unknown break dates. And a common approach in the literature is the so-called quant likelihood ratio test, okay? So we just said it's QLR. It's the QRR test, and that will allow us to systematically identify the most probable breakpoint. So essentially, it's about applying the child test at every single possible date over an interval. And we'll find the one that is most likely happen within that pre-specified interval. So basically, the idea is that we'll consider an interval for some potential breakpoints, okay? So imagine this is our full sample, setting from 1 to capital T, and we also have some initial observations, okay? But the effective sample size is from 1 to capital T. Now, it's impossible to search for the potential breakpoint over the entire sample, because that would result in a sort of biased breakpoint identification. And typically, we would need to trim, okay? We need to reserve some data set at the beginning and also towards the end of our sample. We need to set them aside. We are not going to use them for the breakpoint search. And we're going to use some middle, okay, interval to do our search. And typically, we would trim the first 15%, okay? So we're going to get rid of the not get rid, but we're not going to use the first 15% of our data set and also the last 15%, okay, of our data set. So we're going to trim these parts, okay? So here there's 15% times t, and here we have 15% times t. So these we're going to reserve them, set them aside. What we're going to use is the central 70%. And we're going to test whether each of the time point in the middle 70% is likely having a structural break, okay? So by doing this, we ensure that we have enough pre- and post-break observations to test against. Then the idea here is, okay, suppose this, let's call this as tau naught, okay? So minus 1. And here, this is tau 1 plus 1. Then what really marks the start of our search is the tau naught all the way until the tau 1, okay? So for example, imagine 1 to 100. Then we're going to set aside the tau naught minus 1, which is equal to 15. We're going to set aside the first 15 observations, okay? And we're going to begin our search on tau naught, which is 16. We're going to test whether on the 16, the time index that corresponds to number 16 in the data set, whether there's going to be a break. We're going to do a child test there, and then we'll have one F statistic. And then we'll also test for the next time period, tau naught plus 1, which is correspond to the time index 17. And then we will get another F statistic that, let's call it F2, okay? And then we're going to carry on this test until tau 1, which corresponds to the time index 85, okay? So we have F85. So essentially, we'll have a sequence of 85 F statistics, okay? The tau naught plus, the tau 1 plus 1, that corresponds to 86. And starting from the observation 86, we're going to trim them because that corresponds to the final 50% of our data set, okay? So given the middle 70% in a sample size of 100, we'll have 85 F statistic corresponds to each time point in the middle 70%. then the QLR test statistic is the maximum out of these 85 ones, okay? So the QLR is equal to the maximum out of these 85. Whichever F statistic that has the highest value, let's say the 49, okay? If the F49 is the largest, then our QLR test statistic is equal to the value of the F statistic that corresponds to time index 49, okay? So this is the idea of the QLR test. And because of this test, essentially involves multiple child tests, okay? Here it involves 85 child tests and then searching for the highest, searching for the one that gives the highest F statistic value. This test inherently requires a larger critical value compared to the standard F test, okay? So in the statistical table that I've uploaded for this term, at the very end, you'll see a table, okay? That's called table 14.5. The title is Critical Values of the QLR Statistic with 15% Trimming. This is the table that you should consult for critical values when you're doing the QLR test, okay? So essentially, it's the same idea. The test statistic has a distribution that depends on the significance, has a distribution that depends on the number of restrictions. So you need to search for the row that corresponds to the correct number of restrictions that you are testing. Then, given our setup, okay, remember we're testing whether there's a structural break in an AR1 model. So basically, it's about testing whether the gammas are jointly zero. So here we're testing two restrictions, okay? The Q is equal to 2. So we search for the row that corresponds to the number of restriction Q being 2, which is the second row here. If we're interested at a test, interested at a test in 5% significance level, then the critical value is 5.86, okay? And we can see if we compare this critical value with our standard F test table, okay? If you search for the row that corresponds to the same number of degree of freedom, which is the same number of restriction, 2, okay? 5%, that is 3. 5.86 indeed is greater than 3. So the QLR test requires larger critical values than those for the standard F test, okay? So this is something you should keep in mind. This is really because the test statistic is constructed in a different way, okay? The QLR test statistic is the maximum out of all the F statistic for each of the child tests corresponding to each possible breakpoint, okay? And one advantage of this QLR test is that it allows us to estimate the break date, okay? Essentially, the date that corresponds to the largest F statistic will give us the date where the break happens, okay? So the tau hat is the point where the F statistic is maximized. So in the example we consider here, essentially, our tau hat is 49, okay? Because 49 is a time index that gives us the largest F statistic in our artificial example, okay? So this is the QLR test. And sort of taking it to the example that we've seen on Monday about the GMP growth. And remember, we suspected that there's a structural break because apparently before somewhere around like 1985 or let's say 1990, this seems like to have a higher mean and higher volatility compared to post-1990 where we have a smaller mean and a smaller standard deviation. So if we do the QLR test that corresponds to the middle 70% of our sample, then we can find that, okay, so the line here basically depicts the F statistic, the child test statistic that corresponds to each possible break in the middle 70%. I want to find where we have the largest F statistic, and that happens at the date 1993 Q1, which gives the largest F statistic having a value of 14.08. And this largest F statistic is essentially the value of the QLR test statistic. So the QLR test statistic is 14.08, okay? And we also have two dashed lines here representing the critical values associated with the QLR test at different significance level. We've just seen that at 5%, that is 5.86. 14.08 is much larger than that, so this would lead us to comfortably reject the null hypothesis of no structural break. And also, we can see that our test statistic is larger than the critical value at 1%. Okay, so regardless of the conventional significance level that we're comparing our QLR test statistic against, we will reject the null of no structural break. So there is a break in our data set. And the date where the break is most probable, according to the data set, is the 1993 Q1. Okay, so this is the QLR test. So just some final notes about breaks. So whenever we identify there's a structural break in the underlying data set, we need to be cautious about handling this break. If we only use an AR1 model without accounting for the fact that there is a structural break, okay, so without including the dummy variable and its interaction term for the break, essentially we're estimating the average of the parameters pre and post break. Okay, so what I'm saying is, if we have a break, but we still proceed to estimate this AR1 model without including the dummy variables for the break and its interaction terms, the alpha naught and alpha 1 in this model would capture the average value, okay, for the intercept pre and the intercept post break. Okay? And similarly, the alpha 1 will capture the average value for the slope pre and the slope post break. And basically, this means we will not be able to accurately capture the true effect or the true dynamics before and post break, and therefore, whenever we want to do forecasting based on time series with break, we should include the breakpoint dummies, and specifically, we should only use the subsample post-break to do the forecasting, and that will give us more reliable estimates about the future. So I'll leave it to you to read the slides in a bit more detail. So what we're going to do today is we're going to start talking about trends. We have actually seen trends already, but we haven't really talked about it in a more systematic way. So in the literature, there are two types of trends that are common in time series. One is a deterministic one. So a deterministic trend, essentially, it's a deterministic function of time, okay? And for example, if you have a linear deterministic trend, then this linear deterministic function of time, the ft, is just equal to alpha naught plus delta times t, okay? The trend is deterministic in a sense that the value at each point in time is perfectly known, okay? Knowing that today t equal to 1, tomorrow we know that the t is equal to 2, 50 days afterwards, it's going to be equal to 51, okay? So it's perfectly known, therefore it's deterministic. But given the setup, and we know that the time is changing over time, Okay, the t, it takes different value in time. Therefore, we'll have a time-dependent mean. But we'll have a constant variance because the deterministic trend is deterministic. There's no randomness in t. So if you consider taking the linear trend model, where we have yt equal to alpha naught plus delta times t plus ut, remember, the shock is always an IID white noise with mean 0 and variance sigma square u. Then taking the expected value of y, that will give us the expected value of the entire expression. Okay, alpha naught is a constant, take it out. The delta, again, it's a constant, we can take it out. Multiply by the expected value of t. T is deterministic. The expectation of a deterministic variable is itself, which is just t, plus the expected value of u, our shock, which it's 0, given that it follows an IID white noise process. So we can see that the mean of a deterministic trend only model depends directly on the time index t. Okay. So the mean is changing over time. But if you look at the variance, okay, which is the variance of alpha naught plus delta times t plus ut. Now, by now you should know alpha naught constant, no variance. Okay? Delta, also a constant. T, something that's deterministic, no randomness. Okay? There's no randomness in t. Okay? Only a random variable can have a non-zero variance. Given that it's deterministic, it's perfectly known there's no variance in t. Therefore, the variance of the deterministic trend series is just equal to the variance of the shock, which is sigma square u, and this is constant over time. So the deterministic trend model has a time-dependent mean, but constant variance. Okay? And given the time-dependent mean, the mean is not constant, therefore it's not stationary. But this type of time series is called trend stationary. Essentially, it's stationary around the trend. Or another way to think about it is that we can achieve stationarity by subtracting the trend. So the yt, which is equal to alpha naught plus delta times t plus ut, this is not stationary due to the time index t directly entering the model specification. Okay? But imagine if we subtract the time trend from y. Okay? And this, let's call it zt. Then zt is equal to alpha naught plus delta times t plus ut minus delta times t. So the trend cancels itself out, and this giving us the trend series, the z, is equal to alpha naught plus ut. Alpha naught is just a constant. Ut is the random variable. The nature or the statistical property of zt depends solely on the ut, which by construction is stationary because the white noise process is always stationary. Okay, so this is stationary, which implies this must also be stationary. So we can achieve stationarity by subtracting the trend. And of course, in real life, we never know the value of delta. That means we should estimate the delta first by regressing y on the time index. So that will give us alpha hat naught plus delta hat times t plus the residual. Okay? And it's the residual that it's not having a deterministic trend component because the u hat t is equal to yt minus alpha hat naught minus the delta hat times t. So it's the detrended series. and must be stationary, okay? And so from this analysis, we can sort of see that essentially YT has two components. Okay, first of all, the YT, it has the deterministic trend, the delta T, and it also has the stationary component represented by the Z. So a deterministic trend has two components, a stationary one and also the one that's captured by the deterministic trend. And it is because of this, it only has these two components. Once we get rid of the trend component, the detrended series is stationary, okay? Another example is we can have an AR1 that is stationary around the trend, so-called trend stationary AR1. Essentially, we add the deterministic trend component, the delta times T, into the stationary AR1. So the alpha 1 here is less than 1 in absolute value. So the trend stationary AR1, where we have YT, that is incorporating the deterministic trend plus alpha naught plus alpha 1 YT minus 1 plus UT. This is the stationary AR1 component, given that our alpha 1 is less than 1 in absolute value, okay? And this is the deterministic trend component. So the trend stationary AR1 is stationary around the deterministic trend delta T, which means once we detrended the trend stationary AR1, it will resume stationarity, okay? Anything that is trend stationary, it's itself non-stationary because it's stationary around the trend. The trend makes it not stationary. The trend stationary series can be made stationary by detrending. It's the detrended series that is stationary, okay? So be careful with the terminology. So this is the deterministic trend. And we do not need to restrict the trend to be something that is perfectly predictable. We can also allow the trend to be unpredictable, and this is what is called the stochastic trend. So essentially, the stochastic trend is characterized by the accumulation of a mean zero stationary process, the WT. Okay, so the lowercase w follows a mean zero stationary process. The uppercase W, which is the stochastic trend, is just the accumulation of the observations in this mean zero stationary process. Then, essentially, each random variable W, given that it's not multiplied by any coefficient, you could just think of it as being multiplied by 1, analogous to the random walk case, okay? So in the stochastic trend, each random variable, the lowercase wt, permanently affects the nature of the trend. And given that this w is random, so this allows the trend change from period to be random because we cannot predict what's the next move for the lowercase w. Therefore, making the uppercase w, the accumulation of these random variables, stochastic, unpredictable, random. So a very typical example of a model with stochastic trend is the random walk without drift. So remember, we can write the random walk model, so where we have the AR1 without the intercept, and we have the autoregressive coefficient alpha 1 being 1. This could be written as the sum of all the shocks starting from time 1 up to time t, okay? It's this sum of shock terms that is the stochastic trend here. So essentially remember, the shock, the U, they're stationary. They're white noise, okay? The white noise process is mean zero, so it's the u's, the lowercase u's, they are a mean zero stationary process. And therefore, the accumulation of a mean zero stationary process is the stochastic trend. And we've already seen that this model has a time-dependent variance and also a time-dependent autocovariance. Remember back in lecture 3, where we talk about the random walks, okay? We found that the variance is equal to t times sigma squared u. So the variance directly depends on the time index t. And also the covariance between yt and yt minus h also depends on the time index t. So the random walk without drift has a time-dependent autocovariance and time-dependent variance, although the mean is zero. Okay, if you're unfamiliar with this, go back and check the lecture 3 slides and also check chapter 10 in the lecture notes. So this is essentially the characteristic of a stochastic trend. We have a time-dependent variance and autocovariances. Now, because the nature of the trend is different, okay, deterministic trend, predictable. Stochastic trend, non-predictable. That implies in order to achieve stationarity, we need to use a different approach. So a stochastic trend series can be made stationary via differencing. And therefore, we call models with stochastic trend difference stationary. So the idea here is, if you look at the random walk with drift, without drift, okay, which is yt minus 1 plus ut, okay, but obviously the alpha 1 is equal to 1 here. Then by differencing, essentially the first difference is the difference between yt and yt minus 1. Imagine if you subtract yt minus 1 on both sides of the equation. Okay, then what is left on the right-hand side is just the ut, the white noise component, because the yt minus 1 cancels itself out. Okay, and what is on the left-hand side is essentially the first difference, the delta yt. So the first difference is essentially the white noise, and this white noise is stationary by construction. So the first difference is stationary. Therefore, the random walk without drift achieves stationarity through differencing. Therefore, this type of time series is called difference stationary, in contrast to a trend stationary process where you subtract the deterministic trend directly. And an important distinction here between the two types of trends is that the trend stationary series, the shocks have a transitory effect, okay? The shocks only has a temporary effect on a deterministic trend only model, and the series will revert to the trend over time. As you can see, the deterministic trend model, the y, only depends on the shock in the same time period. The next time period, yt plus 1, that is equal to alpha naught plus the delta times t plus 1 plus the ut plus 1. The ut and ut plus 1, they are uncorrelated, given that it's a white noise process. Okay, IID white noise, they are independent, therefore there's no zero correlation. ut is uncorrelated with ut plus 1. The shock at time t does not affect the shock at time t plus 1, and given that y at time t plus 1 only depends on the shock at time t plus 1, therefore the shock has a transitory effect. Okay? Past shock will not influence the future y. Okay? But of course, in a trans-stationary AI1, the past shock can affect the future of Y, but it will do so in a diminishing rate. The effect is temporary. It will die out eventually. In contrast, in a stochastic trend model or a series, the shock has a permanent effect. As you can see, the stochastic trend model involves the sum of all past shock. Each shock directly enters the model equation for the stochastic trend model and remains there forever. Okay? So the shocks will alter the the shock will alter the stochastic trend series trajectory indefinitely. Okay, so shocks to a stochastic trend model has permanent effect. Shocks to a deterministic trend only model has transitory effect. So this is the difference between the two types of the trends in time series. And of course, we can have series that combine both types of trends simultaneously, as evident by the random walk with drift. Okay, so it has a deterministic trend component, which is captured by the alpha naught times t. Essentially, it's the drift that induces a deterministic trend in the random walk with drift model. So the deterministic trend part represents the systematic, predictable component of the underlying series. And it also has the stochastic trend, okay, which is given by the random walk, the sum of all the shocks. So it captures the cumulative permanent impact of all past shocks. Okay, the sum from s equal to 1 to the lowercase t of the u's. Now, there's one thing here that you have to be a little bit careful about. So the random walk is a special case of a stochastic trend. So remember on the previous slide, we would say that the stochastic trend is the accumulation of a mean zero stationary process. All we require for that stationary process is just mean zero. We impose no restriction on that they're being correlated or they're being uncorrelated, okay? But the random walk, which is the accumulation of the white noise shock, okay? The white noise has no zero correlation. So the random walk is a special case of a stochastic trend in the sense that it's the accumulation of a mean zero stationary process with no zero correlation. In general, we do allow the stochastic trend to capture the observations coming from a mean zero stationary process with autocorrelation, and refer to lecture notes for the example. Okay? And given that the model has both deterministic trend and stochastic trend, the deterministic trend induces changing mean over time. The stochastic trend induces changing variance and autocovariance change over time. So the random walk with drift has non-constant mean, variance, or autocovariance. And typically, in a time series where we have both types of trend, it's the stochastic part that dominates. Okay? So any time series, as long as it has a stochastic trend, it can be made different. It can be made stationary by differencing. Okay? So here, even with a drift, this is the random walk with drift. Okay? As long as we take the first difference, so essentially subtracting yt minus 1 on both sides. Okay? On the right-hand side, the common yt minus 1 term canceled out. What is left is just alpha naught plus ut. The left, essentially our first difference. Okay? So the first difference of y is stationary because it only depends on the shock u, which is stationary. And actually, we've seen this already. Okay? Remember, the real GDP data is not stationary. okay? It has an upward trend and actually also has a deterministic, it has both a deterministic and a random walk, or sorry, the stochastic trend component. And the GDP growth rate, which is essentially the difference, the first difference of the GDP, resembles stationarity, okay? It's fluctuating a constant mean. So we can make the random walk with drift or models with both stochastic and deterministic trend stationary through differencing. And just one final slide before I let you go. So on the slide, you can see that there are different time plots. So on the left, basically we're comparing the deterministic and the stochastic trend. The only part that is new on the left is just that now it includes the deterministic trend, which is plotted in red. We've seen the deterministic and stochastic trend that they are kind of different, okay? The blue line basically is the random walk without drift. So we can see that there's no obvious pattern for it to go up or it goes down. It basically randomly wandered, okay, with no obvious trend. Whereas the random walk with drift is essentially captured by the green line because the drift component induced the deterministic trend. So we can see that the random walk with drift is dominated by the deterministic trend. So if the drift is positive, here it is, alpha naught is positive, therefore the random walk with drift has an upward trend, but because there's also the stochastic trend component, it's random, so it's kind of randomly wandered around the deterministic trend without a tendency to revert to it because each shock permanently affects its trajectory. Whereas the deterministic trend, okay, the deterministic trend only model is stationary around the trend. It's not stationary because it has an upward component. It's growing over time. But we can see that the fluctuation around the upward trend is stationary, okay? It's continuously or frequently reverting back to the trend value. So this is the deterministic and stochastic trend. And we can also see that on the right-hand side, we have a trend stationary AR1 versus a random walk with drift. So remember, random walk with drift is not stationary around the trend, whereas the trend stationary AR1 is stationary around the trend. And we can see that the purple line, which is the trend stationary AR1, it reverts back to the upward trend more often compared to the random walk with drift. However, there's one thing you have to be careful. In practice, it's very hard to tell by just the visual plot whether the underlying time series is trend stationary or whether it actually has a stochastic trend, okay? Especially when the series has both stochastic and deterministic trend. They both tend to look upward, okay? But then the fluctuation could be masked by the variance of the underlying series. Imagine if the random walk with drift component, the variance of the shock is much smaller, then it will look very similar to the trend stationary AR1. Therefore, we should not, okay, make any conclusion about the nature of the underlying time series just simply based on the visual plot. Whether the underlying series is trend stationary or whether it has a stochastic trend, we will need to use a formal hypothesis test to detect this, okay? So I'm going to stop here today. I will finish on the rest on next Monday. Thanks for coming, and just a reminder, the quiz is closing at 5 p.m. today. If you have not done it, you better do it as soon as possible.